So, good morning everyone. I will talk today about how turbulent cascades can be used to generate patterns on scale that are not the largest scale of the system nor the smallest scale. So intermediate scale pattern formation, and I will show you that this involves exotic quantity that we refer to as odd viscosity. This work was carried out in collaboration with our group in Eindhoven under supervision of Federico Toschi, collaboration with the group of Vincenzo Vitelli in the University of Chicago. So the classical picture of the turbulent cascade is this energy injection at the large scale, which is then cascaded through the direct energy cascade to smaller and smaller scales, stopping at the scale where the dissipation kicks in. But now we ask ourselves whether we can change this picture and whether we can stop the cascade at some intermediate scale in a way that is non-dissipative. And then if we do it in a way that is non-dissipative, then we can hypothesize that what might happen is that the energy starts to pile up against this barrier and we get accumulation of energy at some intermediate scale, and in that way we can argue that we have a scale selection and a pattern formation in the flow. And it turns out that there's a natural solution to achieve this, and this revolves around this odd viscosity. So what is this odd viscosity? So in general, when we think about viscosity, we often think about this one scalar quantity in front of our Laplacian in the Navier-Stokes, but that is in fact not the most general manifestation of viscosity. So in general, viscosity is this fourth order tensor that links every possible strain to every possible stress in the fluid. Fourth order tensor, so that's 81 different coefficients in 3D. So let's try to distinguish some different classes. And then a useful distinction that one can make is between even and odd viscosities, where the odd viscosities are the particular coefficients that break this symmetry. And why is this a useful distinction to make? The reason is that one can show that the even viscosities, they dissipate energy, but the odd viscosities crucially do not. So the odd viscosities in the Navier-Stokes equations, they always act perpendicularly to the flow. So they don't dissipate energy.
This question here?
Yeah.
Quickly. This is still true for a system which is rotationally symmetric, but parity is broken.
Yes, yes. In fact, that's another characteristic of the odd viscosities, that they have to break the parity symmetry. So historically, I mean, this is not a new concept per se. So this has been studied in literature where it was given some different names. So it has been called Hall viscosity or gyro viscosity, mostly studied in 2D systems, but there are also a few studies in 3D. So yeah, like I said, it's a bit of an exotic quantity, but it can be found in some physical systems. And there's one example that I particularly like, which is if one composes a fluid where the fluid parcels consist of spinning particles, which is depicted over here. The spinning of the particles, if there's a little bit of friction between the particles, changes the collision kernel, and that gives some parity to the fluid. And then it has been shown that using kinetic theory, that the continuum description of this fluid of spinning particles is a fluid that has odd viscosity. There are other examples like certain MHD systems, just fluids under extremely strong rotation, certain quantum systems that all seem to manifest some kind of odd viscosity. So, okay, now we are still left with a bunch of different viscosity components that are odd. So let's try to restrict a little bit further. So we try to restrict the symmetry of the system. So our first guess was, let's consider the most restrictive symmetry, so an isotropic system. Then it turns out that in an isotropic system, no odd viscosity can exist. So we resort to perhaps the second most restrictive symmetry, which is a cylindrical symmetry. And then it turns out that we can have an odd viscosity. And if we plug this odd viscosity in the Navier-Stokes equation, we end up with this particular term, which I think may resonate with a lot of people in the audience who have been working on rotating turbulence, because indeed it is very similar to a Coriolis force, with the very important difference that there is a Laplacian in front of the velocity. And crucially, what this Laplacian does is that basically it restricts the action of this force to the high wave number range, or to the smallest scales of the flow. So, okay, what does this odd viscosity do if it doesn't dissipate energy? Well, to start to answer that question, we can first consider what it does at the linear level. And then it is very similar to what a Coriolis force does. So it permits this wave-like solutions with this particular dispersion relation. And there is, crucially, there is this kz in the dispersion. So it means that the slow manifold, again, is the 2D manifold, and we can draw up an argument very similar to the one in rotating fluids that is like a Taylor-Proudman theorem. So the 3D triads with non-zero vertical wave number, if the odd viscosity is large, then these 3D triads, they decorrelate, so we're left with 2D manifold that is slow. So this sort of raises the following picture, that in the case where the odd viscosity is weak, we can expect just 3D turbulence and a direct cascade. But if the odd viscosity is strong, then we may expect quasi 2D dynamics that we have seen a lot of already this week. So we understand quite a bit, and we can expect an inverse cascade. So then we need to answer the question, what does it mean weak or strong, right? And we argue that to answer that question, we need to compare the time scale of the constraints, so the time scale of the waves, to the time scale of the eddies. And that is what we do here. So on the left, I show, for the people who are familiar with rotating turbulence, the picture for the rotating case. And on the right is, you can see how that is modified in the case of what we call odd turbulence, so turbulence with odd viscosity. So the eddy frequency just follows from the Kolmogorov scaling, and then the solid lines, they depict the dispersion of the waves. So in rotating turbulence, this leads to quasi 2D dynamics at the large scales and 3D dynamics at the small scales of the flow. But because of the action of this Laplacian for the odd viscosity, this picture is permuted in the case of odd turbulence. And this has an important consequence on the direction of the cascade. So now for this, for the case of odd turbulence, we have 3D dynamics and a forward cascade at the large scales, but an inverse cascade at the small scales. So we have this kind of converging fluxes, and maybe you can already sense where this is going. So these converging fluxes, they come together at some intermediate scale, which is where these time scales cross over. And at this scale, we may expect accumulation of energy and then a pattern formation. And we like to think of this as being a somewhat more general way of achieving a pattern formation that is at contrast with linear systems where there is some linear instability and there's one most unstable wavelength, which is the scale that is selected in the system. And then there are nonlinear interactions maybe to saturate the growth of that mode. But this cascade-induced pattern formation, as we like to call it, is a purely nonlinear effect where there are nonlinear fluxes coming together at some intermediate scale, and that is the scale that is selected for the pattern. So then there's one more complication that we need to consider, which is the forcing scale. So now we can either force at wave numbers larger than this crossover scale. Oh, sorry. That went a bit fast. So we can either force the system at wave numbers that are larger than this crossover scale, and then we may expect an inverse cascade that stops when it hits the crossover scale. But conversely, we may also inject energy at the large scales, and then there's a direct cascade towards this crossover scale where it stops, because either way it tries to cascade in the other direction as soon as it crosses this crossover scale. So let's just first focus on the case of this direct cascade. And then we can make a number of scaling predictions. Yes?
Just quickly. So does the sign of your odd viscosity always positive, or you change from positive to negative, or?
The sign of the coefficient,
Yes.
you mean? It doesn't matter. That's just the parity of the symmetry. Yeah. So then for this case we can make a number of scaling predictions for the different length scales in the system. So the first is this crossover scale, which just follows from this comparison of the eddy frequency and the dispersion. Then we can make a dimensional prediction of how the energy spectrum should be modified, which just follows from assuming that the time scale of the waves is the dominant time scale in the old viscosity dominated part of the spectrum. And then by balancing this modified spectrum with dissipation, we can sort of calculate the length scale at which the pattern saturates. So let's put it to the test. So we put some direct numerical simulations where there is old viscosity on the right, and for comparison there's just the normal 3D homogeneous isotropic turbulence on the left. And okay, maybe it's a little bit hard to see, but perhaps you can already see that the system at least adopts a little bit of vertical polarization in the case with old viscosity. So if we zoom in on these cubes, we can see a little bit more clearly what happens. So there's just the 3D homogeneous isotropic mass on the left, and then here the system with old viscosity, you can already tell that it looks much more monochromatic and a little bit like a pattern. And then we can distinguish these different length scales that we have derived based on the scaling theory. So because of the two-dimensionalization, the features in the pattern manifest as vertically elongated features of a length that is related to the wavelength at which the condensation starts. And then the horizontal length is related to the dissipation, so to the wavelength at which the condensation is saturated, let's say.
Forcing 2D or 3D?
Sorry?
Is the forcing 2D?
It's 3D, the forcing, yeah. So okay, this is all a little bit qualitative, so let's look at energy spectra. So then these are the energy spectra where at increasing levels of old viscosity going up. So we can indeed see that there's somewhat more energy deposited in this intermediate range. And then if we compensate the energy spectra by the normal unperturbed spectrum, we can see exactly in which region of the spectral space this energy condensation happens. And then by compensating also the horizontal axis by this crossover scale, we can see indeed nicely that the condensation happens at this crossover scale that we have derived based on this timescale comparison. So at least over the limited dynamic range that is accessible in DNS, we can say that our scaling predictions are at least not violated. So that's the case of direct cascade. So finally, let's zoom in on this other case, so where we force at the small scales and we see inverse cascade. And then let's start again with pictures. So indeed here we see at a somewhat larger scale organization, but still not a system scale organization. And then these are energy spectra again. So again, we see a deposition of energy in this intermediate scale range, where the diamonds are this K-odd, this crossover scale. Yes, Rory?
Just very elementary. Why is the vertical? What's the problem? The vertical scale is being treated differently because there is what phenomenon selects the vertical in your equations? There's rotation. There's what? What makes it?
Well, okay, so you just need to select one axis, right? So okay, physically can be maybe
so
achieved
you
by a
selected-
magnetic field or a
So
rotation axis. Depends on the system.
You selected that axis.
Oh yeah. It's hand selected. Yes, it's in the equations there was this EZ. So it's like a rotation axis.
Oh yeah,
Yeah.
so you said right.
Mhm.
Okay. Yeah. Okay.
So far it looks quite similar as what is going on in the case of the direct cascade, but now we need to be a little bit more critical and ask ourselves, what is the saturation mechanism, right? Because in the case of the direct cascade, we understood that it was just viscosity that at one point would saturate this accumulation of kinetic energy. But here, since the energy condensation happens at the larger scales, there's no effective dissipation mechanism by the dissipative viscosity. Yes?
Wouldn't it just isotropize when you pass your critical scale?
That would be a k-squared scaling, right? But this is clearly more flat than k-squared, right? So it turns out that the answer is related to also something that we have seen earlier this week, which is this flux loop. So we can distinguish two classes of fluxes based on the sign of the helicity of the different modes in the triads. And then there are the triads with like sign helicity and the triads with a different sign helicity. And then we see that basically in the case of these of this inverse cascade condensates, that they balance out exactly, and that the net flux into the large scale vanishes. But there's it's a result of a detailed balance between the homochiral flux and the heterochiral flux. So it's completely different saturation mechanism than in the other case. Now, finally, let me make one more sidestep. So we can argue that these odd fluids perhaps can be used as a model for different systems in which this sort of cascade-induced pattern formation can emerge. For example, as a result of a different source of waves, maybe there's a second sign a second sign definite invariant that is conserved over a limited range of scales. So there may be a whole zoo of other systems that can exhibit this cascade-induced pattern formation. So then we thought it would be nice to generalize the dispersion of these waves, because they might not all have a k-squared dispersion, right? And then, okay, in the language of viscosity, we can understand this as perhaps odd hyperviscosity with some arbitrary exponent p. And then here we show sort of the other extreme, where the dispersion is not a k-squared, but is very steep. So the steepest we could think of was just doing a step function. And then we can see that, okay, indeed our condensate also happens very sharply at one wavelength, and there's a very strong peak in the spectrum. So let me conclude. So we have shown how the non-dissipative arrest of the turbulent cascade at intermediate scales can lead to a pattern formation in the turbulent fluid. And the odd fluids, they are a beautiful example where we can derive a bunch of scaling theories, but we will argue that the phenomenology is much more general, and we'd be very excited to see all the different geophysical, astrophysical situations where an effect like this might occur. And if you would like to read more, I can refer you to our paper that came out last week. And with that, I would like to thank once more my collaborators, and I'd be happy to take any questions from the audience.
time for one quick question whilst Rachel sets up. I think you were first, actually.
Okay. Just the point that in the end it isotropizes actually once you go over your critical scale, because before you have this sort of helical modes, and the inverse cascade is just because you have plus interactions.
Yeah.
And once you cross over into the critical scale, like the large scales are just, they become isotropic, so you have all kinds of plus, minus, minus, plus, so.
It isotropizes at the large scale, which is a little bit funny, right? Because in most other cases in turbulence, like we can play with the turbulence at the large scales, but whatever we do always vanishes as we go to the very smallest scales where everything isotropizes because the eddies become so fast and it will always become 3D. But this is different. This is the opposite, if you will. Yeah.
Okay, thank you very much.
Okay.